Okay, I think we're going to go ahead and get started. So I'm going to hand things over to Pavel to introduce our speaker for today. And I have this in case you want a cheat sheet.
Okay, well, hello everyone. So I think today I'm very happy to see our great SMU friend coming back to give us a seminar about his recent work. Now, for those of you who don't know Keping, so Keping got his PhD from Beijing University in 2014, and then he came and finished a PhD degree in our theory group here at SMU between 2014 and 2019. And then Keping went to University of Pittsburgh, where he's a postdoctoral researcher in a very well-recognized group working on phenomenology of elementary particles. Now, Keping, I would say, well, you want to know him better, right? So if you, one way to know him is to come with us for dinner tonight. But he really has a very diverse range of interests. He's a master of all trades, and now he worked with me on the structure of the protons and continues working with me on this. He also did some research on models of non-standard Higgs boson interactions. And today he will tell us about his other recent work, which is dedicated to bread and butter physics at muon colliders. So please welcome Keping.
Okay, so thank you, Pavel, for this nice introduction. It's always good to come back to meet our old friends, all of you. So today I will talk about these Symbiont Gliders. Of course, there is a lot of things we can do about the muon collider. I will mainly focus on the physics side. Of course, there is a lot of technology side. I think Jimbo knows much better than me about that. So we will focus on this physics. This work has done in two scenarios. First one is about this standard model physics at high energy muon collider, in more general electron collider. And of course, we want to move forward. I will also cover a little bit about BSM-30 and muon collider. Take this muon-Higgs Yukawa coupling. So we done this work was done with my postdoc advisor Tao Han and his student Yang Ma. And this BSM is done also with few German friends. So let's this is the outline of this talk. We mainly two parts: electroweak PDF, also this is BSM Higgs. So let's first ask about why we think about Symbiont Glider at high energies. Of course, it's a great of interest to think about something always beyond what we can go. And so especially about this, everybody knows this proton collider, hadron collider, and electron collider. We are familiar with that. And muon collider, it's great to have both advantage of hadron collider and electron collider. So it can get a very high energies, which is the proton collider can give us. But simultaneously, it can also give us a very clean environment to measure something we want, especially when we think about the BSM physics. So electron colliders, it's great for us to probe this short distance physics. And the thing about the history, we have scholarly history about electron collider. Many big discovery it has made by this electron collider, like the charm, tau, or even gluon was discovered at electron collider. And of course, in the future, we are proposing some future electron collider like FCCEE or CEPC, or even this have been discussed about 30 years about this international linear colliders. And the muon colliders have these features. Also, muon colliders as other advantage we have mentioned about this can give us very high energy, like up to TeV scale. And the more optimistic, it can even give us 30 TeV, or even someone think about this 100 TeVs. And this was provide us a great advantage to explore this BSM physics. Like we can measure this multi-boson Higgs or even multi-Higgs production at high energies, which is can never be achieved at like a proton collider at a very clean background. So I list some of them here, but we can discuss them more if we want. So let's move forward. So think about what's a possible high energy muon collider to think about the size of these colliders. So here I list about these few colliders we have already below very familiar. First one is this first size of this formula. You can say this kind of size. And at the same time, you can say this Brookhaven, roughly same size. And you can say this is current LHC, this light yellow, light blue circle. So currently, this LHC roughly 26 kilometers. So think about this Higgs factory for muon collider. You can say we can only have very tiny size we can reach this get this muon colliders built. Of course, think about this even higher this such as 400 GeV muon colliders or 3 GeV muon collider. You can see this size. So we don't need to build some big tunnel in order to make this. So you just do the existing one, even the Fermilab Teratron tunnel is already getting enough to us to just to fill this muon being there. We can get this externally up to this high energy, this energy. Yeah, and the luminosity I listed here, which we are talking about. Of course, there are currently all these are just estimation. So we can optimistic to side to have some energy dependence on luminosity, which goes as your energy squares behavior. Of course, conservatively, we have some technology issues, which will constant this luminosity, but still we can get this high luminosity like 10 inverse anobars. So that's the basic setup for us. So let's think about what we can do based on this muon collider. So first thing we should do, everybody should be aware about that two mechanisms or two kind of physics will show up in muon colliders. One is about this vector boson fusion, one is annihilation. I show us some typical standard model cross section like WW production, TT bar or TT bar Higgs production at high energy muon collider at multi-TeV energy range. So you can say on the left plot, there are two kind of curves. One is downward, one is go upward. That's very typical. So one is about this annihilation. All of them go downward because this 1 over S behaviors, just S channel, or you have 1 over S suppression. So at high energy, when your energy is going high, all this crossing decreases drastically. But on the other side, we also have fusion, which behaves as logarithm of your energies. Right? So if we can have very high energy as a muon collider, you can see all this vector boson fusion crossing goes very quickly, and very soon you is dominated by your cross-section production. So all of this standard model process will dominate by your vector boson fusion process. Similarly, we have listed some others like the QQ bar, or you can think about the jet production and we have think about some realistic detector configuration, like this is corresponding to 10 degrees of your detectors are in the forward directions. So the behavior is the same. So the question is for us, we have this enhancement because of this vector boson fusions. To think about WW as a reference, and we have this the high energy electroweak physics or low energy QED or QCD, this one. So you can say this one. This is about this WW fusion or WW production. Similarly as here. So that's roughly the size of give us this the rate. So the question I propose here is how can we treat this W and Z standard model particles at high energy lepton collider or properly because of this vector boson fusion or this logarithm collinear enhancement. So that's so we should provide us the answer to this one. So think about electroweak physics at high energies. So because the energies become so high, all the standard model particles like WZ essentially become massless. So this massless give us exactly same behavior as QCD. So we get this logarithm enhancement. So the electroweak symmetry just restored, gradually restored. So we get the fully symmetric standard models at high energies. So all these gauge bosons, all these gauge bosons actually exactly behave like your Higgs. So we have Goldstone equivalence theorem, and of course we have a violation, Goldstone theory violation, which is behaves like your the population to your mass. So this is exactly the same which shows up already in QCD, like high twist term behaves as power suppression of your lambda QCD. So we know this splitting behavior. So we have already be familiar with this factorization of the QCD. So we have quark Coulomb PDF. Similar situation will also happens at this electroweak sector. So we will similarly have electroweak PDF. And for the initial state radiation, for the final state radiation, we will have some similar as the fragmentation function, or which can be simulated with particle showers. We will talk about it later. And other aspects which doesn't show up in QCD is about this. QCD it's nice symmetric SU2 symmetric which is unbroken. However, electroweak physics, it's first one is chiral theory. So all this left-handed and right-handed the Fermi behaves very differently because the interaction is different. So when we talk about electroweak boson scattering, so you need to be aware about this polarization of the electroweak boson also with your Fermi. And another interesting thing about this Yukawa coupling, because top quark Yukawa is roughly order 1, which is significantly enhanced compared to others, which is not like legible, which doesn't show up in QCD, or we never see that. So that's a general picture about electroweak physics at high energy. So think about this factorization just to mimic about this QCD splitting. So how we do this splitting behavior? So usually we can think about the process like something A splitting into B, C, this which and in the collinear region B, C it's almost get the same direction as A. This is the final state radiation, or for similarly for the initial state radiation is the right one. So the cross section in this collinear limits can be always factorized as your hard part cross section, which behaves as like this is partonic crossing sigma x, and another part which is collinear part, which is you can say this A and split into B, C, similar for this initial state radiation, and we have this kinematic variable. This collinear part can be behaved at here. You can say it's always then at high energy, everything is just to behave like your collinear factorization, and the factorize you have this momentum fraction of your daughter particle come from your mother particles. So count about this dimensionless. The splitting behaviors either behaves as a QT with some QT of the particle like BC, or which if we have think about this gauge boson like WZ, they have mass. So usually your gauge boson is cut off by your mass. So when we talk about this collinear behavior, so we have either KT cutoff or transverse cutoff or mass cutoff, which is behaves differently. To validate this factorization in theorem or factorization formalism, we have to be aware about that. Your observable should be simple, very safe. You cannot reconstruct some divergent observable which is not can be never measured. Of course, in order to make this work, the leading behavior should be coming from collinear splitting, and that's what gives this factorization of your picture capture your main physics, and which exactly happens in the collinear in this vector boson fusion. So just to think about it, we have talked about the initial state radiation and final state radiation. So we should treat as them. Then this the initial state radiation to be with some as your parton distribution function final state deviation, we should with some logarithm enhancement with as your fragmentation function. And the leading order behavior of splitting, which is already done 30 years ago about this, we call this effective W approximation. And longitudinal behavior of your remnant of because this mass of effect in this scenario can be nevertheless ignored. So this will give us power suppression as your think about this W mass or Z mass, which gives us same order of magnitude. And this one can be treated as a Goldstone equivalences. And that one is exactly the same as this high twist effect in this QCD scenario. So we will see that with how this in my follow-up slides. So think about this. Let's come back to this effective photon approximation or effective W approximation, which exists for almost centuries. So think about this photon radiated from your lepton, which is the most simplest case we can say. Such as think about your electron or lepton collision with some target like A here, and the fusion process which is coming from your photon radiated from your beam particle, your lepton. So the lepton collide with your target can be factorized as your hard partonic cross section convolute with your photon PDF, and the photon PDF is well treated, which is certainly proposed by Fermi and followed by Weiss-Collinear. So this is also called Weiss-Collinear approximation. And the behavior I show up list here. And in this same scenario, the effective W in the gauge SU2 gauge or standard model, so gauge symmetries can be similar treated with the effective W approximation, which is show exactly behavior as this one. You have this collinear splitting curl comes of your logarithm enhancement, and this logarithm enhancement give you this big cross section at high energy. And I show this diagram. You can say then think about the lepton collider or high energy muon collider. What happens there? Actually, it's exactly it's kind of gauge boson collider. So you mostly are collide this gauge boson together, and then you produce all the outer particles. Exactly happens as the proton collider. You have proton beam comes and all this collision are hard crossing coming from your parton inside of the proton. So that's how mimic or how you think about this electron collider or muon collider, lepton collider, based on our knowledge of the proton collider. So this is which we know for 30 years already. So let's, but I have given you some caveat about this electron or the standard model. First one is the standard model is a chiral theory. The chiral theory, you have this chiral interaction, which is violates CP symmetry. So think about this PDF, such as you have polarized dependence in your beam and also your parton, like your vector boson. So when you do this CP transformation in both phase of the beam particle and your parton, you will not get this exactly same PDF because your chiral theory, chiral violation behavior. So for the QCD-like or QED-like in a more simple case, we can have a well-established unpolarized factorization, which you can sum over of your polarized, get an unpolarized PDF. And then usually for this, for the QED or QCD PDF, we already talk about the unpolarized parton distribution, but we should not the case anymore because all of your PDF should be polarized. Now this is first feature we should be well treated in this scenario. Another scenario which is also never show up in QCD is about this gamma Z or this interference between different partons. Think about this same process. You can say, and this is just to heart of this the convolution of you get complex conjugate with another part. So you can have interference between the intermediate particle gamma and Z. And then you can say in this diagram, this color diagram, you can have one side is gamma from your initial beam, another side is Z from your initial beam. So in this sense, when we do factorization form about this diagram, we will end up as a parton as gamma z simultaneously in your parton. So that's corresponding to the interference which gives us your mixed gamma z states. So we have this interference, the PDFs which never show up in QCD or QED case. So this is another feature. And of course, one big problem is about this factorization or this QCD is good because QCD is symmetric. QCD symmetric give us nice features about this the gluon PDF. Think about the gluon in your QCD. You can never distinguish gluon colors of gluon or quarks gluon. So what is observable? What is good observable in QCD is always color blinded. Color blinded, then you construct the observable of your case. So you need always sum over all your color, and then you get the formulate or your singlet color singlet observable, which is show up in the detector. However, this is not the case in the electroweak theory because the electroweak you can well establish neutrino or from electron. And similarly for W and Z, you can observe W and Z well resolve them. And however, think about this W and Z in gluon. In gluon, it's just different colors. You have 8 kind of gluon, so you need sum over all the gluon. But this is not the case in electroweak sector because W and Z they show up differently. So this gives us a big problem because when you have this kind of diagram, you can say in QCD case, you need sum over these 2 cases and get cancellation done. But this is not the case in the electroweak theory because you can say this splitting electron beam give you neutrino PDF, but the virtual diagram give you electron PDF. And they are separated in 2 different PDFs. So this is a big problem for this one, which called block logic violation, which requires us to reconstruct your PDF in your as QCD case. We have to think about this singlet case, which sum over your electron. And then the divergence can be cancelled in the singlet, but not in your this color violation like this triplet cases. Go ahead.
So on the other hand, the advantage here is that these PDFs are perturbative.
Yes.
Right.
Right.
So therefore, it's just the equations get more complicated.
Yes.
But you can in principle you can calculate
right.
everything.
Right.
So,
What happens to interference effects when you have radiation?
Interference effect with radiation, you mean radiated a gamma and radiated Z? Is that what you mean?
They will be differently polarized, right?
Yes. Then you need to have different polarized PDF. And then your PDF becomes very complicated because you need to formulate a big basis, which is refer to different PDF. For example, you have this one, you have polarized PDF, which cannot be as your this one.
So can I ask another one? So just like in QCD, you can apply some power counting.
Yes.
So some of these terms will be what is called leading power, but some of them will be suppressed.
Yes.
Right. So that does the same. Are the terms that we are showing here? They are what is called the leading power terms.
Yes.
There is no suppression like 1 over q squared.
1 over q. We do have that term, but that term will not as collinear enhancement. You don't have collinear logarithm enhance. And then of course when you formulate this is not the full picture. This only captures the logarithm enhancement term. You will plus some power suppressed term, which is shown as a constant. So when that's why when your energy become large, all these power suppressed terms just become negligible. So this is we have talked about this electroweak PDF. So we should go beyond the effective equivalent photon approximation or effective W approximation. So we need to come up with a full standard model PDFs So you can see all this the splitting I showed up here. So think about the leading order, you can have split into photon, and the sub-leading splitting, photon can split into your lepton. Simultaneously, you can have split into quark. So and quark can go further split into quark and gluon. And when your energy goes even far above your electroweak scale, like Z mass, when you cross this Z mass threshold, you can have also this W and Z as well. So finally, all these standard model particles become your partons as quark and gluon inside of the proton. So in the end, we have everything, every standard model particle as your partons. So that's a full picture about this. So let's just do this is some little technique about how we treat this one. So we just only have just DGLAP. We need to sum the logarithm, which is done by this DGLAP equation to sum logarithm into your PDF. And we have clearly 3 regions, and we choose some kind of threshold below some QCD or the region like lambda QCD, which is some standardized scale, but it's quite slightly different with lambda QCD, because lambda QCD is characterized with this 200 MeV, and we should be think about it a little bit further. So we just simplify it. So we just divide it into the different regions. And then below some QCD range, which we only have QCD. So in this sense, below the QCD region, we only have quark and we only have the photon PDF or some lepton PDF. But above this QCD region, which quark and gluon enters. And another standardized is electroweak scale. We choose your Z mass as just distinguish these 2 regions. Above the electroweak scale, we have all this everything. So this is a 4 pictures. So let's ignore this technical one to think about this more interesting about this results, how this PDF behaves at a high energy. So first one, as I mentioned, about below your QCD, below your electroweak scale, we have QCD. Yeah, so we have quark gluon we have photon PDF, we have valence PDF, like this valence quark in the proton case. Simultaneously, we also have quark and gluon PDF. So here I just list U and D quark as example. And we show this for electron beam or the muon beam, and we choose 2 standardized scale like 30 GeV or 40 or 50 GeV. You can say this is 1/S behavior or log X behavior. Of course, the photon is the first radiated from your lepton, so photon PDF is the biggest one. And at this X going to 1 limit, because that's full moment fraction is carried by your lepton. So in this region, it's almost mainly coming from your valence. So valence will dominate as your X's moment fraction going to 1 limit. In another soft limit, everything shows up at here. Similarly as the Symbiont gliders. So I give us some number about how large the size of it is. So think about this 30 GeV for electron case. At this 30 GeV, you can see almost all the moment fraction is carried by your valence, and subleading as your photon and C and the quark gluon, etc. Let's go one step beyond above the electroweak scale, and then we get all this electroweak enters. So we have all these standard models, the particle as your parton. So we have W there. Simultaneously, we have as I mentioned about this polarization effect. So we have to distinguish W and Z. We also have to distinguish transverse and longitudinal W as well, because they behave very differently. And longitudinal W or longitudinal WZ, which is carries about your this Bjorken violation, which does not have logarithm enhancement, because all this effect is just your mass effect of your W gauge boson or WZ gauge boson. So this behaves just to like Bjorken scaling. So we call this Bjorken scaling restoration, which is constant at a high energy. So this does not enhance at all. But you can see longitudinal will involve, because longitudinal becomes much larger than your, or transverse becomes much larger than your longitudinal. So we also be aware about this electroweak sector. give you a correction to your low energy side, like your U quark, D quark PDF, which is due to the QED effect. So at high energy, we should consider about 4 electroweak theory, not just QED one. But I give us some numbers like about 15 or 20% level about your scale uncertainty, which quantify the difference between your different scale choice, which is here show these two scales here. So that's this PDFs we have got. So let's make some prediction about this. What will happen at high energy electron colliders? Think about this. We just to think about this electron colliders in a 3TeV, which is kind of clique. This clique collider setup, and think about 10TeV muon colliders. And we show up some parton luminosity before we make some prediction for this process. We show all this parton combination like your beam particle, valence quark, valence lepton, and we so all these combinations here. You can say, then we show some keep in mind about size. But of course, this is the valence one will show up as your take full energy of your electron of your lepton beam. So it will blow up at your with your all this energy. Square root of tau going to one limit. It means that all the energy is carried by your lepton beam valence quark. But with the soft limits, like when this moment fraction goes smaller, all this parton shows up. Of course, the largest one is coming from your photon, one photon and one your valence lepton, and subleading is gamma, and all these other subleading. So this gives us the size of the parton luminosity. But keep in mind, this QCD interaction, the strong coupling is much larger than your QED interaction. So consider about this one, we would expect the sizable, or which we will show this about this in the next slide. How large your size of your QCD interaction at high energy colliders will behaves. Think about this. We just come up some kinematic cards, which is such as we show this colliders about 5 degree or 10 degree of your detector. Of course, we should think about some kinematics about your threshold cards about your final state, or some PT cards, some very generic cards. So then we could give us some feeling about the cross section. Let's take about DGLAP production example at high energy electron colliders. So similar as before, we show us electron collider at 3T at a few energy scale of muon colliders. So you can say the largest cross section of the DGLAP production actually is coming from the quark initiated process, which is exactly this parton behaviors. So you have partons inside of your lepton, and this one will significantly contribute to DGLAP production at high energy in lepton colliders. So both in the electron case and in the muon case. And in electron case, it's even more significant because the logarithm enhancement is even larger because this electron mass is much smaller. So you have much larger logarithms in this electron case. You can say this one, you can compare this total DGLAP production compared with this gamma, the photon initiated process. You get 2 to 3, actually it's 2 magnitudes larger than your gamma, which is only QED effect. So your QCD effect, which are like the quark gluon partons initiated, which gives you 2 magnitude larger. For this muon collider case, you get 1 magnitude larger than your photon initial process. And then think about the standard model electroweak physics. We have mentioned before. We take this WW production cross section as your benchmark, as your number. So you can say the DGLAP production initiated by your quark gluon partons, which goes even larger. So you have 3 magnitude larger than your WW productions. So if we measure some electroweak physics or BSM physics, all this jet production will come as your background, contribute to your this process. So we have to treat this one very carefully if we want to get a very precise prediction about this new physics model. But however, there is good news about that one. It's the kinematics of the different process behaves very differently. It's not so something SMEFT. Let's think about some kinematic distribution, like this invariant mass or Wheeler distribution of your digest production, or this WW process. You can see clearly that one. All this jet production initiated by your quark or gluon partons peaks around this low energy scale. So if we go to solve, very soft, like your invariant mass requires to be very like few tens of GeV, all this junk will come together. But if we require your threshold to be higher, think about this WW invariant mass, the threshold which is 160 GeV, just slightly beyond that one, 200 GeV, take example. You can see all this standard model of the digest initial process will excluded. So this is exactly the idea. We can, if we want to study some BSM physics or electroweak, like WW electroweak physics at high energy scale, we have to think about this all this kinematic card to exclude all this junk. So one basic requirement is just to impose some invariant mass card, which will give us the safe scenario, will give us we want at high energy. So this is the invariant mass card and this the repeated cards, repeated distribution. You can say for repeated distribution, we show up these two scenarios. One is about this mu annihilation, another is about vector Bose fusion. Annihilation process is very sharp peak around this when you have this which exactly peak around the repeatedly going to zero limits. However, all this vector Bose fusion will spread out. But this keep in mind this your annihilation will be kicked by your one photon initial state radiation, which is coming from this ISR. That's why you get this shape or slightly spread out, which is of course not spread as this your vector Bose fusion process or this parton process. So that's the pictures. Other kinematics like transverse momentum or energy or your rapidity of your parton of your jet product process, everything behaves the same as before. So we should think about this some kinematic to be hard enough to in order to get suppress all this jet or this soft jet events. So another thing about this, you can see the boost, which characterized by your energy of your thing about W. Your W, so it's boost. How large you boost we have to in order to remove this one. Actually, it's not very high. Just to when your energy of your W, kind of 100 GeV is enough for us to here I give us some number which 200 GeV, kind of same scale. So this is the idea about what's this low energy standard model digest plug you want. So as we have already shown that one, we need to move to high energy. Then we can study some BSM physics or electroweak physics at high energy. So let's think about some electroweak scattering process. Like here, I just to list some electroweak parton distribution or electroweak luminosity at high energy. Take 30 TeV muon Glider example. As same as before, you can have this annihilation or valence muon, and all this vector parton electroweak parton luminosity comes later. So I here similar as before. I give us some moment fraction. Keep in mind how large about this the size of this electroweak PDFs will be have. Here I take 3 TeV or 5 TeV as your scale to quantify how large. So you can say W boson only take off 1% of your parton moment fraction of your beam particles. So that's the basic size of this one. So let's just to make some prediction in based on this electroweak PDF. Here is the result. We have already shown this WW before, which show up once again, but this is different from previous one because previous only coming from gamma fusion, but now we have all this electroweak as your parton as well. So we have WW fusion, Z fusion, gamma Z fusion as well, all enters into these pictures. Similar as others, others, all of them will receive contribution from the electroweak PCDF or electroweak partons here included by here. So everything now is the parton, and everything is kind of fusion process now. Oh, actually, I also show up as before this annihilation, which highly suppressed before. So you can say think about this WW production example. You can say this is 1, 2, 3 magnitude larger the fusion process than your annihilation. So all this cross section mainly coming from this fusion process. So actually, one to conclude this subsection with that with all this standard model or this heavy scattering high range laboratory behave like your proton colliders or hadron colliders. Lepton collider give us kind of gauge boson collider, actually, which is collide gauge bosons. So that's the picture of this high energy muon collider, high energy lepton collider. So same as before, we show that some decomposition of different partons like WW or gamma Z, etc., or compared contribution to the whole total cross section. You can say one, of course, gamma still contributes biggest one, and all others come secondary, like WW fusion or WR fusion. We need to decompose into different polarization. And this can give us the size of different parton decomposition, and this give us the kinematic distribution. Similar as before, you can say I should normalize this distribution. All these fusion processes show up as your threshold region, and but along the collider energy region, which is as this your beam energy scale, is mainly coming from your annihilation. So that's so for this imagine mass and rapidity, same as before, we have sharp peak about this the rapidity here, similar as WW or the Higgs, or just repeat. So let's move to next topic. Do we have some question based on this? What we have showed here before here? Okay. So we have we assume everybody knows the standard model Higgs. We want to take advantage of the high energy muon collider to do BSM physics, to search new physics. So we know about the annihilation and vector boson fusion, which we're familiar already. So at high energies, actually, the collider, we have see this all these gauge boson fusions. Actually, that will give us a great advantage if we want to put such as Higgs physics. So all this Higgs will coming from this scattering and longitudinal. Think about this longitudinal behavior, the Higgs boson or longitudinal gauge boson, which is exactly your Goldstone. So you have Goldstone equivalent theory, which is give us the longitudinal double gauge boson can be characterized by your Goldstones. So we know that the muon collider as gauge boson collider. We also know the discrimination of the annihilation and vector boson fusion. We should take advantage of that to separate these two scenarios. Previously, we have emphasized this vector boson fusion, but now we want to switch another one to emphasize its annihilation. So let's see what we can do here. So one example is that this muon-Higgs coupling, which we will show up because we consider about muon colliders. So we can measure this muon-Higgs coupling at great precision at muon colliders. So let's come up some models such as this Bach or extra dimension models, which can give you deviation of your muon-Higgs coupling. You can see based on your standard models or prediction. So we show up here. You can see one is this. We show just to show about this the rounding of your muon-Higgs coupling or the muon-Higgs mass, your mu mass rounding in based on scale. So we will here is the standard model prediction. You can see it's round as here, and then you can see we normalize to here. This is red line. But if we have new physics contributions like this different models, which can give us significant deviation from your standard model prediction. So the goal of us is just measure, can we measure this difference at high energy muon colliders? And that's the goal. So let's say how far we can go. So first instance, we need to quantify the BSM physics. We need to know how much is the difference between the standard model and this BSM physics. Let's come up with some theory, which we will use this effective theory parameterization. We think about this how we can parameterize this effective theory. Of course, we can use some nonlinear Higgs effect theory, or we can use some standard model effect theory. We just to quantify all this your BSM model, BSM contribution with your new operators. Like for this Higgs effect theory, all this one coming from the nonlinear realization of your Higgs boson. So you will say that this I give us an example about this lepton-Yukawa coupling, which is mu here. You can say all this mu-Higgs coupling will receive correction based on this coefficient. All these coefficients is coming from your BSM physics. Similar as this standard model effect theory, you can just take some black box. So all these black box will contribute to this BSM contribution to your mu-Higgs Yukawa. And then all this mu-Higgs Yukawa will behave that this Wilson coefficients entered into the coupling, and you normalize into your standard model prediction, which is this Y1. Standard model Yukawa, or here we just this is kappa. You just take the ratio with the BSM contribution with respect to the standard model, then you get this new physics contribution, which as your coefficients. So we just want to say how much we can determine these coefficients at high energy muon collider. So let's see this contribution between the standard model and the BSM physics. So we have seen that before about this annihilation, the fusion process, annihilation process. First one, let's compare about this Higgs cross-section, the cross-section of the multi-boson production. I list all the possible multi-boson productions, the triple boson or the four boson production. And on the left part, you can see we have already seen before. One is going downward, that's annihilation, which is down upward, that's vector boson fusion. At high energy, this you can see, similar as before, the vector boson fusion will dominate. But we know this kinematically, they are totally different because the kinematics, the behavior is very different. We can take advantage of that to separate these two parts. Here I show this standard model prediction and the BSM contribution. Here take some such as take this kappa. We showed this previously before. This kappa is coming from your BSM, and they think about some benchmark such as we take kappa which equals 0 or 1, and which corresponding kappa equals to 1 will exactly correspond to standard model prediction. And we can think about construct some model to kill this Higgs Yukawa. So if we can think about some Higgs coupling, have mu-Higgs, mu-mass, but without Yukawa coupling, which corresponding to this coupling going to 0. That's corresponding to this dotted line. You can say, and then the difference will become very significant at high energy collider, the high energy muon colliders. So this is the triple boson production and the four boson production. You can say even more sphere. You can say so at high energy muon collider we can measure this difference, and then we can determine this Higgs coupling at very great precision. So if we find this difference at high energy muon collider, we can discover new physics. So that's the basic ideas here. So let's characterize this BSM physics. Actually, I showed up this what's the behavior of this all these different channels like for triple boson production. In everything actually behaves the same. Use the Goldstone equivalence theorem. So the only difference coming from your symmetry factors, because your W and Z boson they have different symmetry factors. And then you normalize to think about the W Higgs, which is the largest cross-section triple boson production. So you normalize them, then you can all this one actually behaves similarly, just a standard model, just a standard ratios. So here I give a ratio, and this numerical value which grades is quite well. So that's show up this difference between your standard model prediction and the among different channels. So similar as the four boson production, actually as before, you can say actually all this deviation from standard models just to quantify by this one parameter, which is kappa. So let's determine this kappa. Think about our 10 TeV muon gliders. So we take this WW Higgs production as an example. So this I show some kinematic distribution like theta, this angle distribution of your boson, or emergent mass and this kind of separation between the different bosons of three of them. You can see first of all, let's focus on this emergent mass. And see, we have seen already before, the better boson field, all of them show up around your threshold. So peak around this low mass soft region. But annihilation will peak all around peak of all your collation energy. So they will peak about the 10 TeV collider. So you will peak around this 10 TeV region. So if we can think about some kinematic cause, such you require your boson to be like 80% of your condition energy. So just to select events here, and then all these vector boson fusion events can be just suppressed. So we can focus on this annihilation, and then we can measure the difference between your standard model prediction and your BSM physics. So I show you this black curve and the red curve. Red curve corresponds to standard model prediction, and black curve corresponds to the BSM. But you can see there is significant difference between these two curves. So we can measure this difference. So all other distributions come similarly. So let's similarly for this Higgs production, we have all these similar features. But let's compare some numbers. So as we can put some cards, some typical cards here, and then count the events. How many events we can measure at 10 TeV collider based on the luminosity we have shown us before. So you can say at a 10 TeV muon collider, we measure this WW Higgs. You can say the standard model events corresponding to this one, which will give us a few hundred events. But BSM events will give us very significant, which is 2-3 times larger than your standard model prediction. So then you can see which will have a bigger as this signal over background ratio. And for this the Higgs production, the signal background is even bigger because your standard model events is much smaller. But the BSM contribution, which comes the same size as your WW1, then if we focus on this one, we can even get better sensitivity. So let's quantify this one. How can we precisely determine this BSM physics? So we think about this define your signal, define your background. So let's do this systematic scan, how precise we can go. So we just to show some different deviation, some contribution from BSM one. Of course, depending on parameter choice. Let's parameterize them as one single parameter kappa mu. Just to this one is corresponding to the standard model, the two corresponding to the BSM and one. So you can smooth transition from this standard model prediction based on this BSM scenario. So you can see all these colors are smooth transition from this color plot. And a different color like solid, dashed, or dotted one, and they are corresponding different cuts, kinematic cuts. So we can measure this difference, which then let's see how much we can quantify this one. So this is coming from our money plot. So if we require your signal, think about this deviation, your uncertainty of your standard model background, which you often think about Monte Carlo. So the uncertainty of your standard model will often behave like your square root of your event. So that's your uncertainty. The signal is mainly coming from the BSM physics. So think about how many sigma we can get. So we can just choose 2 sigma or 5 sigma. Think about the 2 sigma events, 2 sigma deviations, then we can come up how much of this the muon collider will determine this standard model, this BSM contribution deviation. So this one is the result. You can say a different energy which we can measure this the deviation between your standard model and BSM one up to very precise. At 30 TeV, we can even get 1% precision as your standard model, as your muon-Higgs recover. If we discover some the events which beyond this one, that's exactly corresponding to BSM, which cannot be explained by your standard models or with your uncertainty. So think about the 5 sigma deviations, and we just to get some events not very big. Then we can get very easily to get this 5 sigma deviation if we compute this collider. So the conclusion will come. So if we translate this mu-Higgs coupling deviation between the standard model to some BSM scale. So think about this standard model EFT parameterization, all this corresponding to your new physics scale. Then you can say, actually, for this 30 TeV, we can reach the new physics probe to 100 TeV. It means that you can use 30 TeV muon collider to constrain BSM thing up to 100 TeV. Okay. So that's why we are get very excited if we can build these muon colliders. So let me summarize. So I talked 2 scenarios. One is about this what the standard model physics will behave at high energy lepton collider, especially high energy muon collider. And one we talk about this BSM physics measurement at high energy muon collider. Take this mu-Higgs coupling as examples. So of course, the one thing about this, all this standard model particle will becomes partons. Exactly, they have to show say as QCD case in the proton case. Then we have high energy muon collider is just an electroweak gauge boson variant of the high energy. The proton collider like high energy LTC. So for the mu-Higgs coupling, if we have this mu-Higgs collider, we can measure this mu-Higgs coupling at a great precision. Yeah, and we can probe new physics up to 100 TeV if we have the 30 TeV muon collider. So let me stop here to take questions.
It seems of all those radiated.
Not really. The thing about no matter how high energy it is, think about you can boost the muon into your rest frame. So if you have some BSM particle which must be much heavier than your mu-Higgs, than your mu mass. So in your rest frame, the muon cannot decay into some heavy particle. So you just boost it. So that will not affect the decay. But of course, radiation, that one will affect. But that one, we have to show this standard model one. Think about this one. This is a standard model particles like gamma, Z, etc. So if we have some BSM particles, so it will come much below here, even smaller than this. So all of these new physics particles inside of your lepton should be smaller than the standard model sector. Standard model sector, we have to show exactly how large a size it is. So yes. You can build some model like L mu minus L tau, then you can radiate this gauge boson which mu decay, and then it's not decay, it's just radiate a new gauge boson, and then your mu will become tau. Then you have this new partons, new gauge boson, which should be much smaller than here. And you, of course, here we let's think about, go back a little, exactly the same. Here we show this electron. This you can say at this electron collider or muon collider similarly. You can have this anti-electron, We can also have this anti-muon inside of your electron, inside which should be roughly the same size as this one because it's coming from the gamma radiation. Gamma is splitting with your electron. Here you can think about tau. So the tau roughly size behaves like this one. So if we have new gauge interaction, the bosons, so it will, here I give you size. So that one contribution will be much, much smaller than this one.
Well, are there any other questions since you're deferring to me? Well, okay. I can. Yes. They'll interfere with each other. Just go ahead. Yeah. There's no one on. Oh, okay. All right.
There is another complication compared to PCBs. That there are electroweak boson couplings involve mixing matrices, both for quarks.
Yes.
As well for neutrinos, and for neutrinos they are not well known.
Yes.
So what do you do here? So with the mixing matrices.
Mixing matrix, you mean CKM? No, that's becoming extremely. First one, the effect is extremely small. With a lot of factor. I have shown this. You can see here this example. This electron, this is muon beam. We have this, of course, the biggest common valence one, because electron valence, this black curve. This is a neutrino. Neutrino effect is here. But of course, this is not coming from this this mixing matrix. It's coming from this gauge boson decay or gauge boson interaction. Just think about this W. Okay, W will interact and split into your neutrino, which is this. And then we can think about this one and of this one, the kind of PM cell matrix will inside of this bin, inside of this band, between this solid curve and dash curve. That's one thing. Then we need to very precisely determine how large is the deviation and to give us quantification. So that effect is negligible here.
So are you going to post this PDFs on the LHE PDF? That was my question.
Yeah, it's already there. No, we didn't publish the PDF that, but it's everything is there. We just haven't. We want to write some big paper, which is, and then after that we will release this.
Related to that question, there's a small group of people within the community that are interested in an intermediate machine.
Yes.
A muon-ion
collider,
say Brookhaven.
Yeah.
As an upgrade to the electron
Right.
collider. So in doing simulations, presumably, if you said the lepton PDFs are already available in LHAP.
Yeah.
So in principle, we should be incorporating these into our simulation.
Exactly.
Okay,
yeah.
great.
That's very simple.
Yeah.
Yeah.
We'll be doing that. Okay, great.
Actually, I use this PDF as I work with Pablo. I load this LT PDF, and all this is based on same convention, just to release, and then everything can be incorporated. Very easy.
So related to this as well, this is a perfect slide to talk about. These are all pure theory that we're looking at here, right? Okay, great. Have you attempted to then extract these from existing E plus E minus collider data and see if they agree with this? You expect they should, right? But has anyone tried to do that? I mean, for instance, gamma star, or gamma star, Z star interactions at E plus E minus.
I have this one which backup. Very fortunately, I put it here. You can see this gamma. Actually, this was done by click setup 3-TeV electron colliders. Of course, gamma will induce into hadrons. And you can see this is simulation done by experimental group. You can see the spectrum of this as PT and theta. All this activities becomes theta goes very small. So I put here, one is about PT 4-TeV as this is horizontal, one vertical is corresponding to 5 degrees. So of course, below these two cars, all this will enters. And beyond that one is in this small circle, or this one, actually no effect at all. low effect of all. So that it does it. So if we want to go to this region, of course, we have to incorporate this one. Have to, because all this junk is coming from this non-perturbative interaction, which we have to extract from data. This is just to measure this data in the experiment and then feed it out. But for this high energy region, which is the perturbative region, which it doesn't at all, doesn't it? So this is blank, which exactly which I show here in this region.
So what's the region where we need data then? I got a little lost.
It's in the extremely forward region, like this thing.
So lower left corner.
Yes.
Okay.
Yeah.
Low PT, low angle.
Right.
And there's no I mean, for instance, I know that Babar and Bell were plagued by gamma star. Not being able to simulate that very well.
Yeah.
I've wasted a year of my life to simulate gamma star interactions and just gave up because the code was basically from some guy's thesis from 1970s.
Right.
That's early 1980s, and everyone was using it, and it was really outdated. No offense to that guy's thesis.
Is that a Gini pig? Gini pig written by
15 years since I did that.
By this guy, this Barclow or not
It was an
Barclow?
experimental person. Maybe Barclow. That does ring some bells.
This guy, Daniel Stewart, should be that one.
Okay.
Yeah, exactly.
That looks familiar.
Yeah, exactly. Okay. I know that code. I did use that code to want to extract something. It's not, of course, that well written, but it's doable.
It's doable.
Yeah.
Well, what I'm wondering is, can you take even low energy scattering data or data from SLC and infer find a point on one of those PDF plots and see if it compares to the theory?
Yes.
You can do that.
Yeah, we can do that one.
Has anyone done it?
No.
Okay.
No. Yeah. I'm thinking about that one, but I need to talk with this Daniel Stewart and to do this joint one, because the first one, this always range well simulated already. But we should smoothly transition. Currently, these are just disjoint with two different scenarios. So in between, we need smooth transition and then get some consistency. That part isn't done yet. Also, there is big uncertainty there. Even when you can think about this, this is two scenarios. One is PCR simulation. One is called SLAC, done by Paskin and the Barclow, etc. They have done this one. You can say, of course, kind of agreement, but if we look in more detail, they will give you significant deviation, not as precise as the high energy part.
Occasionally heard about neuron gliders.
Yes.
Do you know a timeline for those kind of plastics?
Yeah, this question Paskin always talk about this one because, of course, they are pushed by different group. Paskin doesn't want to. He always want to push this IOC, this linear glider, and his answer is very elective, but we don't think in that way. Tau and by other group like the Brookhaven group, it's about kind of 30 years, hopefully. We currently, the big advantage we have, bigger breakthrough made is about the cooling. And they demonstrate it's possible, it's feasible, doable in the future. Of course, there is a lot of another technology like intensity, of how you do this, make this high luminosity intense. That one.
Can you tell us what the status of the cooling of the neuron is? One of the limitations is the fact that it lives for a fixed amount of time now, and you have to cool it down to small size in order to make any sort of collision.
I'm not sure for that part, as I didn't get into the detail about this.
I would say that this is a good opportunity for us to request a speaker from the mice experiment, which is trying to address exactly this issue with Fermilab, right?
Exactly.
So, But if you're not sure of the status of that, that's an opportunity for us to get somebody from mice to come and speak.
In fact, this is the opportunity to advertise the upcoming SMEFT
some summer study where this.
He gets paid by the advertising.
But please consider participating. So we were talking this morning that, well, essentially it looks like the ILC may not happen, but then the question is, what is the next major goal for the US collider physics? Muon collider would be good force, but then all these technical issues need to be discussed in addition to the discussion that is present in the SLOMAS white papers, and we need to come up with a message from the community whether we think it is feasible or not. And so that I think muon and muon collider probably will be two major problems.
That makes a lot of sense. Yeah, they are kind of heavily related to each other because it all bears on beams.
Yes.
Cooling beams bunching. Yeah.
Mm-hmm. I list, of course, I can list more, but I just list 3 of them. Slow mass activity, these 2 papers, you can take a look, which summarize this muon, including the accelerator stuff and also the physics side.
I want to come back to this question of the decay. I mean, in particular, tau electron in this picture would have different branching fractions depending on energy, isn't it?
Branch fraction.
I mean, the rate of decays to different final states. That's the atomic decays and also hadronic decays.
Yes, but that branch fraction, of course, does not depend on how your energy of tau. The branch fraction is always your property of your lepton, no matter tau, mu, and then you can always boost it into your last frame.
DSM picture gives you additional interaction, right?
Yes, I don't have the drawout diagram, but actually think about this. You can see here. Think about this is the tau or mu. Then you can have BSM gauge bosons here, If you talk about branch fraction of that, actually it's just static. So you can always boost it, which is boosted into your rest frame. And of course, there is BSM contribution, which is exactly this splitting picture, which is not decay branch fraction. It's a PDF.
Yes, so I think in other words, you include the full kinematics and the branching fraction.
So there's a propagator which is central surface.
Yeah.
You go back to the rest frame of the object.
All right, well, let's go ahead and wrap up there. As Pavel said earlier, Keping is around until Thursday.
Yes.
So there's lots of opportunities to grab him for a coffee or lunch or something like that. He's sitting in Fred's office, and that's it. I completely forgot. I can't forget. Fred's not here, so it's a perfect place for him to set up. So you can look for Keping up in Fred Olmos' office on the 2nd floor. Okay, let's thank Keping one more time.